Hello, everybody. Welcome to a 2.9 logarithmic expressions. I am Coach Meidenbauer. This is it's AP pre-calculus. I'll get that right. So we're going to go over some log stuff. What's big is how to write from exponentials equations, how to rewrite them into logs and vice versa. So here we go. Exponential form, you can see that on the left side, it's b to the a equals c. And a and c are going to be constants, and b is going to be our base. Base has to be positive, but not 1, because if it's 1, it don't make much sense. If you can kind of see a relationship between our logs and our exponentials there for all of these. I do use a little bit of a technique that helps me because I ain't so smart in memorizing that stuff. It's called the loop method. So I start with my base, and then I loop it, and then I'm going to equal that. So this is going to be log base 3 of 81 equals 4. That's how I rewrite stuff. I just use the looping method. I think it's easier. So it works going from logs to exponential. Start on the base. So 7 to the 2 equals 49. That's how I rewrite these, but I think they're easier. Some log expressions. If you ever see a log with no base, it just means it has a base 10. But logs are related to exponentials with just how I showed you. You can see that relationship. So what we're going to do is we're going to find some values here. So examples without technology. So we're going to go ahead and find this one right here, log base 5 of 125. So this is, again, if you just have this memorized, that's great. That's what I do. I put a question mark right there. I'm like, all right, what is that? I don't put a variable because sometimes we have variables in here. So it's 5 to the what gets me 125. So, all right, so 5 times 5 is 25 times 5 is 125. So it's 3. So the question mark, that is 3. So this equals 3. Okay? I do the same thing for the one right below it. Equals question mark. 8 to the what gives me 2. So 8 to the what gives me 2. I have to think. All right, 8 to the what? If I'm going smaller, I need that base to be, or that, not the base, I need the question mark there to be less than 1. So 8 to the what? Now, if I don't know it, I'm lost. Rewrite 8 as a base. Well, this is going to be 2 to the 3 question mark equals 2 to the 1. So I have 3 question mark equals 1. What's the question mark? Divide by 3? Oh, the answer is 1/3. Moving on here. Again, there's a little base 10 right there. So 10 to the what gives you 10,000. That looks like that answer is going to be 5. Because I got 5 digits. I'm trying to think. Am I right in saying 5? Why am I drawing a blank? I don't know. 2 is 100. 3 is 1,000. Oh, because I'm drawing a blank because it's 4. I can't count the zeros. This is 4. If I would have that would have helped me out a little bit. Okay, that's 4. Log base 10 again here. How do I get from here to 1 over 100? So 10 to the what gives me 1 over 100. Again, we're going smaller. So, well, this is going to be a fraction. So I can rewrite this 100 as a 10 to the negative 2. So what's my question mark then? Oh, this is negative 2. Okay. So here's some examples with technology. I don't have the technology out right now. All right, I just pulled up my technology so that we can have it here in a second. But there's 2 ways to do this. I'm going to show you both ways. One is just straight up using your TI. I'm going to go ahead and share this tab right here. So the TI, if you hit alpha F2, where the window one is, it gives you this table right here of all these cool things you can do. If you go down to log base, you literally can just type in what it says, and then you're golden. So this one is going to be 2.9 2.047. There's also something called the change of base formula. Okay, so the change of base formula is when you take the top and just write it as log 27 all over log 5. You get the same answer. So let's go ahead and see if that's true. Or if I don't know what I'm talking about. So if I just do, the log buttons are next to the 7. So log of 27, make sure you put that parentheses in there, divided by log 5. You'll get the same thing. And there you go. Kablamo. Same answer. So that is 2.047 or 48. Doesn't matter. I truncate. That's how I do things. So 2.047. Okay. So you can type all that stuff in your technology. I don't really feel like going back and forth to do all this stuff. So you can do that. You know what? I just will. Log base. Oh, I'll share this tab. Log base. Was it 8? Was it 5? It's 8. Log base 8 of 5. I got 0.773. I truncate. The logs are just hit this log button right here for 110. Get that answer, 2.041. And then do the same thing for the other log. And you're going to end up with 0.732. Okay. There's also an ln button right below log. That probably is going to become more common to you. I don't know if it's in these notes or not, but the ln button will get similar to that. I can also use the change of base formula back here on the regular one. I can use the change of base formula using logs or ln's. So I could, for this one right here, I easily could have did ln of 27 over ln of 5. In calculus, we use ln a lot, so I'm just used to using ln's. Okay, so that's everything you need to know about logs for right now and just finding the values. Here's a cool new thing. No sarcasm there. We have two graphs of population here, and we're going to use something called a logarithmic scale for the first time. So the left one is a graph that you're used to where all of the outputs are equal intervals whenever you graph, and you're used to that. Like the interval increases by 1,000 every time. So if these data points right here show an exponential growth right here. Okay. Now the one on the right, this is a logarithmic scale where the first graph is the first output is 10 to the 1. The second one is 10 squared, which is 100, then 10 to the third. What makes this a bit more unique here is that you can see that when you put some type of growth, like exponential growth, onto this right here, that you will get a nice little lovely linear line, it looks like. So what it does, it changes exponentials into linears, which is pretty nifty. So here is a logarithmic scale, a coordinate plane. So you can tell that those little lines just represent just 1/10 of whatever we're doing. So this first line right here, this is 1, this is 2, this is 3. It gets tighter and tighter as you get closer and closer to 10. After 10, that one's now 20, 30, and it goes 40, 50, 60, whatever. It gets a little bit tighter. Then up here, this is going to be 200, 300, and go on, so on and so forth. So we can plot all these points. So they got at 120, that's going to be right up here. So this is going to be letter A. For B, that's 2, 300, and I labeled that right there. And right there is B. C is 3, 2, and there is C. And what's really nifty about this is that you're able to look at coordinate B and C are so far apart on a regular scale, but on this logarithmic scale, we're able to compare them and look at them on the same exact axis, which is pretty neat. Before I look like a nerd, I'll not say this is neat anymore. So for D, we're at 415, so it's between 10 and the 20, so it's going to be right there. That's D. And for E, that is 5 and then 350, which is going to be just above the 300. So that is E right there. So there you go. That is everything you need to know about logarithmic expressions just for right now before we start solving or anything. Do not forget to like and subscribe.